Hey everyone, welcome back. We are here with yet another office hour with Chegg. Once again, I've been partnering with Chegg all semester long to bring you Organic Chemistry 1 tutoring. We're doing these office hours here. Feel free to check out the QR code on the top left corner to see what other courses the Chegg has been bringing you in terms of office hours, other topics, math, and other things. Been doing Organic Chemistry 1 here with me. Last live stream of semester. Hopefully, we will be coming back in the fall if you're taking OChem in the fall. But this is the last one here as the semesters are drawing to a close. Everybody's looking at final exams coming up here if they're not occurring already. So this will be the last one. I've got a few problems prepared for you guys, so feel free to follow along. And the chat is live, so I'm accepting questions from the chat. Please keep them Organic Chemistry 1 related. Feel free to ask questions about the problems I'm going over, or feel free to ask questions about any other Organic Chemistry 1 topic, anything that you want to know about. I'm happy to take tangents as necessary if there are some good questions to answer. So thanks everyone for joining, and let's go ahead and get started. So first up here, we've got just a few transformations. Obviously in OChem, given a starting material and some reaction conditions, tell us what you get. This is going to be a very common type of question. So what do we have here? We have this methyl ester, and then we have a phenyl Grignard reagent in excess. So we have, it's a benzene ring. It's right, this is this. Right, we have a phenyl Grignard reagent. So what do phenyl Grignard reagents do? The carbon that is bound to the magnesium will act as a nucleophile, and it will attack a carbonyl carbon. That's typically what a Grignard reagent is going to do. So let's have that attack right here. And then this is going to pop up here, but because we have an ester substrate and we don't have a lot of room, so let's just do all this all at once. Let's bring that that pair of electrons back down, kick off the methoxy. We are going to get this. Right, so methoxy here, and we can do, right, methoxy is gone. So the one Grignard reagent, and MGBR will be complexed to that. So the, and we can do, that'll be a plus charge right here. So one Grignard reagent attacked, but it says we have excess, right? Excess means that a second equivalent can react, because once again, we know that Grignard reagents attack carbonyl containing compounds, and we have regenerated that carbonyl. So we went from an ester to a ketone. So we can have another phenyl Grignard reagent attack. We do have the appropriate amount stoichiometrically to let this happen again. So let's pop this up here. Now we have two phenyl groups, two phenyl rings here, and then we're going to have, let's put O minus there, and then we have this ethyl group there. So this ethyl group is the original ethyl group on that starting ester. We've attached two benzene rings to it, two phenyl groups there via the phenyl Grignard reagents. And then the last thing here is the aqueous acidic workup. Right, we know that. So you're doing this Grignard. This is all one pot, right? You've got your substrate in there. You're going to add your Grignard reagent, probably via syringe. You're going to let this go. It needs a little extra time because we've got two equivalents of the Grignard reagent reacting. Then once we believe that all the substrate has reacted efficiently, we can go ahead. We're going to toss in some ammonium chloride or a weak acid to do some aqueous acidic workup, because we want to protonate. We want to protonate our oxyanion there, right? We want to isolate the alcohol product. And that will be this. So Grignards make alcohols, we know that. And we know that with an ester substrate, we can add 2 equivalents of the same Grignard reagent. So that is that one. Let's do the, let me just check here if anyone had any questions. Bucky asks if I'm going to be doing Orgo 2. I don't know. I'm available if Chegg wants to do these again in the fall. I'm available for Orgo 1 or Orgo 2. I will say, however, Grignard reagents typically taught in Orgo 1, sometimes Gilman reagents as well. If not, certainly in Orgo 2, they have to be covered. But Grignard tends to be on the earlier side. So oftentimes in Orgo 1, but it does depend on the institution. But yeah, I'm available for all of these topics. In the meantime, here we go. We just did some Grignard right there. Okay, going on to this, we have this alkene and we have MCPBA. This is metachloroperoxybenzoic acid, right? So we have it's a peroxybenzoic acid. So instead of a benzoic acid with an OH there, it's got another oxygen, right? This is what is meant by peroxy. It's OOH. Peroxy refers to an OO covalent bond, 2 oxygens covalently bound, and then metachloro. So at the meta position, we have a chlorine atom. So we don't have to. You should maybe be able to draw the structure of MCPBA, but you don't really necessarily have to. All we have to do is memorize what it does, and what it is MCPBA is the classic epoxidation reagent, right? This is how we make epoxides, or one of the ways, but it's a very simple way to make epoxides. And so if we're going to make an epoxide here, we know that the 2 bonds going to the new oxygen atom have to be cis to one another, obviously, because they're leading to the same atom, right? You cannot have a wedge bond and a dash bond going to the same oxygen atom. That doesn't mean anything. That doesn't make any sense. They're leading to different places in 3-dimensional space. So we have to have that. And then what that also means is that those methyls must be pushed back like this. You could have done the oxygen on the dashes and the methyls on the wedges. Doesn't matter. Same molecule. It's just the flip side, right? If you pick this up and put it on the other face, you'd have the other version. So that's all it is, right? When you see MCPBA, you know that we're making an epoxide. And then just be aware that we're going from sp2 hybridization, right? These are trigonal planar sp2 carbons. We're going to sp3 tetrahedral carbons. So you do have to now show dash and wedge bonds. So that's important as well. Great question, Ryan. So in this case, there's no stereochemistry to speak of, because there's no right. If we had, let's say, like this, let's say there was that. Now you'd be talking about a mixture of stereoisomers, right? Because now this would be different. If you have the methyls on the wedge and the oxygen on the dash, that would be a different molecule. And so you would certainly have a mixture of stereoisomers. You might be able to favor one over the other due to sterics, but you would certainly have a mixture. But in this case, we're not worried about that because that's not there, right? We have not generated a chiral product, so that's the only one there is. But yeah, good question. Always be thinking about stereochemistry, right? Especially if you're going from sp2 centers to sp3 centers, you have to be aware: are you generating chiral centers, and if so, are you getting a racemic mixture, right? Or is there some stereoselectivity to discuss? So very good. Okay, going on to this one here. Now, what are we going to do? We've got an alcohol and we're reacting with PBr3, right? So we have this sequence, four steps here. PBr3 is our classic compound for converting alcohols to alkyl bromides. So we're just swapping out that hydroxyl for a bromine. That would occur with inversion of stereochemistry if this were a stereocenter. It is not, right? If this were instead on one of the other one of the internal carbons, that'd be Carl center, and we'd have to invert the stereochemistry, but as it is terminal, it is not, so we don't have to worry about it. And so that's that one. And then now we're going to react with elemental magnesium. So obviously we're generating a Grignard reagent here, and magnesium will insert itself into that carbon-bromine bond, thereby reversing the polarity, right? This is the first example of Umpalung chemistry that we typically learn in organic chemistry, right? And so what that means is that it's where we're reversing the polarity of a particular bond or functional group. So normally with alkyl halides, the carbon that bears the halogen is partial plus, and the halogen is partial minus, typically, right? But by inserting magnesium in there, so metal atoms do interesting chemistry. If you go on to take inorganic chemistry, you'll learn about oxidative addition, reductive elimination, things like these different kinds of mechanisms that metal atoms can do. But just for now, we just need to know that magnesium is inserting itself in that carbon-bromine bond. And because magnesium is less electronegative than carbon, that now means that the carbon is the partial minus in that covalent bond. And so what that means is a Grignard reagent is a source of nucleophilic carbon. We have a carbon atom with electron excess. It can act as a nucleophile, and it can attack carbonyl containing compounds like this one, like benzaldehyde, right? We have a phenyl ring and a carbonyl, right? CHO means this, right? This is benzaldehyde. And so this is going to attack right here. So we go from the carbon itself right here and then pop that up. And let's draw it like this. We have this guy, and then we just added a 4-carbon Grignard reagent, 1, 2, 3, 4. And now we have this. Yeah. And so that's what we did, right? We added a 4-carbon group here. That's going to be this. So, right, those 4 carbons, that's those 4 carbons, right? This carbon right here is the one that used to be connected to magnesium. This is the new bond right there. And when we made that bond, we kicked this pi bond up onto the oxygen to get the oxyanion. And now we do our aqueous acidic workup. And this time we do have stereochemistry to speak of. So let's be very specific and show both of these possible products. And this will be a racemate, right? Because when the Grignard reagent attacks benzaldehyde, the benzaldehyde is a completely planar molecule. It is 100% planar, right? And so when the Grignard reagent attacks, it can attack from this side or that side. There's nothing differentiating one face from the other. The activation energy is absolutely identical, approaching that carbonyl from this direction or this direction. So it will do so in equal proportions. Statistically speaking, when we zoom out, macroscopic amounts of collisions in the flask there, you're going to get exactly 50-50. And so this one is the S, this one is the R, and we're going to get 50-50 racemate there. Okay, let's see if I missed anything. Congrats on the MCAT, Group 141. Okay, so moving on here, we've got this hydrogenation. So this compound has 1 double bond and 2 triple bonds. And so we need to think about when we do hydrogenation, notice that it says excess here. So we're going to try to hydrogenate as many pi bonds as possible. And this is being done under Lindlar's catalyst. So what can this do? We have what does H2 excess do to double bonds, and what does it do to triple bonds in the presence of Lindlar's catalyst? Okay, so we know that for let's see, how do we want to do this? Yeah, let's have these be wedges. So for the double bond, we're just going to get rid of that, right? If you hydrogenate, we're just going to get rid of that. And then over here, we're going to go, oh, wait, actually with Lindlar's, never mind. With Lindlar's, we're going to just leave it. We're going to leave that one. But we have the triple bonds, and Lindlar's is the way to go to the Z alkene. Okay, so we're going to go up here. And now we're going to go, we have 2 more carbons. And we're going to go, whoops, let's do that. Z alkene. Z alkene. Okay, so Lindlar's catalyst is the way to go. We're going to stop at the Z alkene, so that prevents us from going all the way to the alkane. If Lindlar's catalyst were not present and we were just hydrogenating as much as possible until it was fully saturated, we would be getting rid of all of the pi bonds. But because of Lindlar's catalyst, we're going to the Z alkene from the alkynes. So the alkene we don't touch. We can't go further than the alkene. And then over here, we go to the Z alkenes. And it does look a little funny right here with the wedge bonds, but these are sp3 centers. So we do want to show that, right? There are implied hydrogens right here. So it's just a way of showing the stereochemistry around this carbon. But then once we get to this one, we are sp2, and then sp3. So that's that one. Okay. So I want to do a little bit of spectroscopy because this is a very, if you guys have final exams coming up, it's very important to be able to do spectroscopy stuff. And especially there are problems like this where we are given combined IR and NMR data, and we need to be able to glean information from each in order to make an assignment. So we have IR data, proton NMR data, and we have a formula, C5H10O, right? And we need to find the structure of this. We have the molecular formula, but we need the structure, right? And so let's look at the IR first. Okay, the IR first, what can we get from this? Now remember, from around here to the right, this is the fingerprint region, which is a little bit harder to get info from. You can do it, and you will later, but for now, we're looking over here. This is just the saturated CH stretch, and that's going to be present in almost any organic compound, so that's not really too interesting. But over here, we have a carbonyl stretch. So it's right around 1700. Right. This is where it shows up, and it's always a very long and thin peak. A long and thin peak at this frequency is a CO stretch. It's a carbonyl stretch, which simply indicates that there is a carbonyl in the compound. Okay, so that helps because we know that there's an oxygen atom, but we need to know what kind of oxygen atom. So is it a hydroxyl oxygen? Is it an ether oxygen? Is it a aldehyde or ketone? So by identifying the carbonyl stretch, we are eliminating certain possibilities. It's not a hydroxyl, it's not an ether, it's got to be either aldehyde or ketone because it's got to be in a carbonyl. Right. And then the other thing we need to understand is the degrees the degrees of unsaturation. And so if we have C5H10, that equals 1 degree of unsaturation, right? Because normally if it's totally saturated, that would be CnH2n plus 2. So CnH2n equals 1. CnH2n minus 2 would be 2 degrees of unsaturation. A degree of unsaturation means a pi bond or a ring. And so that's dictating, right? We're learning something, the number of hydrogen atoms present. tells us also something about the structure, right? And so 1 degree of unsaturation makes perfect sense with the carbonyl because there's a pi bond in the carbonyl. That's our 1 degree of unsaturation. So other than that, we have hydrocarbon and a carbonyl. That's all it is. We know we have a carbonyl, and that carbonyl represents the 1 degree of unsaturation that we just said. So if we have a 5-carbon molecule, what are the possibilities here in terms of the structure if we know that we have a carbonyl? Well, okay, we could have this aldehyde, right? We could have we could have this ketone. We could have this ketone. That's about it, right? I guess you could put a methyl over there. Let's just see where we get with these three, because now we want to look at the NMR spectrum. Okay, so let's take a look at this. Now, there's many ways to do this. The two most common ways to do this would be to look at possible hypothetical structures and make predictions about what the spectrum ought to look like if the structure were true. Or you can look at this, you can look at the spectrum and identify fragments from the spectrum, because we have integrations, we have splitting patterns, right? Look right here, we have a triplet we have a singlet integrated to 3. So that means that we probably have a methyl group, and we probably have that methyl group it's those protons are not split by anything. So that methyl group is probably next to the carbonyl, right? So that alone kind of already helps us make our decision here, because in any other case, you're going to have protons on these carbons that are being split by adjacent sets of protons. So why don't we do this? Let's just go here. First, let's say how many peaks we would expect. Right. If this was the structure, we would have one. Let's call that 1, 2, 3, 4, 5 peaks, right? Because we'd have the aldehyde proton, which would be quite a bit downfield. Then there's no implied hydrogen here. We'd have 2 protons there, 2 protons here, a little more upfield, 2 protons here, a little more upfield still, and then a methyl there. So 5 peaks. That looks like that's not a match because we have 4 peaks, right? What about over here? We would have 1 there, 1 there, 1 there, 1 there, 4 peaks. So that looks like that makes sense. What about this one? Well, there's a symmetry here, right? And because of the symmetry of the molecule, those methyls would generate the same resonance. And then these protons would generate the same resonance. So that one probably doesn't work either, right? Because that would have 2 peaks. So based on number of peaks alone, let's go ahead and assume it's going to be this guy. So let's get rid of the other options. And now let's make our assignments here, right? Let's make predictions about what the spectrum should be, and then verify, right? So we've got 3 protons there, and this should be split into here. Let's just draw them all first, and then I'll make the assignments. So these guys should be integrated to 3, and it should be a singlet, right? Because there are no neighboring protons. These guys should be integrated to 2, and it should be a triplet, because we've got 2 protons next door, n plus 1 rule. So 2 plus 1 is 3, should be split into 3 smaller peaks, should be a triplet. These guys should be 2H, and this should be a multiplet. It's got 3 next door over there, 2 next door over there. So that should be 6 smaller peaks. Let's just call it a multiplet, right? Very heavily split. And then right here, 3H, and this should also be a triplet. Okay, so let's see what we have. And then also, which should be the most upfield and which should be the most downfield? Definitely this one should be the most upfield because it's the furthest away from the oxygen. Then going slightly more downfield would be this one, because it's a little closer to the oxygen, but not next to it. And then over with these two, this could be a toss-up. Maybe we don't know, right? And it's not that important to know. We don't have to flawlessly be able to predict every single chemical shift or anything like that. We know that these two sets of protons will be the most downfield. We don't know necessarily one over the other, but these will be more downfield than the other two. We know that because they're adjacent to the oxygen. So they're closer to the oxygen than these other protons. So let's see if we have that, right? So here, let's call this, let's go A, B, C, D. So we have a 3H triplet, and it's the most upfield. So that's got to be D, right? That's these ones. These are the most upfield. They're the furthest from the oxygen. Split into a triplet, integrated to 3. That one works just great. Then we have, here's a multiplet. So this is just a little zoom in of here so that you can see there's 1, 2, 3, 4, 5, 6 smaller peaks, which is perfect. That's what we said, right? It should be integrated to 2, and we have 1, 2, 3, 4, 5 neighboring protons. 5 plus 1 is 6. So it should be integrated to 2, split into 6 smaller peaks. That's great. That matches just right. Then over here we have it's a singlet integrated to 3. That matches perfectly with this methyl over there. 3 protons, no neighboring protons. Integrated to 3, singlet, that is going to be peak A. Then we have the remaining 2H integrated to 2. It is a triplet. We can see that. And it happens to be the most downfield. So we're learning that this set of protons is more downfield than this set. So that, if we didn't know that, we know that now. And there's our assignment. So what did we do? Right? It's very important to be able to trace the logic here because we are given a molecular formula, C5H10O. And we know that we could draw a bunch of different structural isomers without looking at any of the data, right? And there could be 10 of them, right? Because we're talking about, it could be a hydroxyl, all the way places the hydroxyl could be. It could be an ether. Where's the ether oxygen going to go? But that's why we look at this data, right? You look at the IR first for one reason and one reason only. You look at the IR spectrum to know that there is a carbonyl in the compound. There's the carbonyl stretch right here. And again, it is this long and thin peak at this very particular wavelength, 1700, 1800, around there. We look at that, go, there is a carbonyl, done with IR. We don't care about IR anymore. That's the only thing that we were trying to get from it. Now that we know there's a carbonyl, that dramatically narrows down the number of structural isomers that are possible. That will be the answer here. And we drew a few. We drew the aldehyde, and we drew 2 possible ketones, because you could have the carbonyl on carbon 2 or carbon 3 of the straight chain pentane. And then, honestly, all we did was predict the number of peaks that we would expect for the 3 structures. Remember that we got 5, 4, and 2. And already doing that, we didn't even have to go in and check for the integration and the splitting of every single structure. Just by predicting the number of peaks alone, we figured out probably, and we weren't positive, but we said, okay, we're pretty confident that this one is it. If we went in there and then we found discrepancies, that the integrations and the splittings and the chemical shift weren't lining up, then maybe we'd go back to the drawing board. Okay, what if we take something and move it around? I don't know. Maybe there was another answer possibly, but it looked pretty good. And then we matched everything up. For each resonance, we saw that splitting, integration, and chemical shift all agreed. So all of the data corroborate this structure. And so that's the answer. 2-pentanone. 2-pentanone was the answer. All right, let's see. Did I miss anything? Whoops. Well, a lot of questions here. This is going to take a second. Okay. Oh, Bucky asks about complex splitting with cis-trans double bonds. So the thing about alkenes, the pi bond restricts rotation, right? Because with a pi bond, the sigma bond is direct overlap of those orbitals, and as long as those orbitals are overlapping, the bond exists, so they can rotate freely. But the pi bond is about the lateral overlap of the unhybridized p orbitals, and so those can only overlap if they're parallel, right? If they start, if the bond starts rotating, they're no longer in a configuration where they can overlap. So the pi bond restriction is rotation is restricted, and what that means is that if you have two groups, right? If you have a proton here and a proton here, they're actually fixed with respect to the two groups over here. So let's say you have an oxygen atom right here. The proton right here is objectively closer to that oxygen than the one on the other side, than the one that's trans to it, right? And so that will actually generate a discrepancy in the chemical shift of the two alkenyl protons. So when you have an alkene, so almost always the protons on the same carbon experience the same chemical environment. And that's pretty much due to the rotation of sigma bonds. But when you have an alkene, you introduce the possibility of two protons experiencing a different chemical environment because the rotation is restricted around the pi bond. It can't rotate, otherwise the p orbitals won't overlap and you won't be able to have a pi bond. So very good question. TFA Lazarus, this is organic chemistry 1. Yeah, typically organic chemistry 1 will get to this point in spectroscopy. If we can block this frost to you guy, that would be great if that hasn't happened yet. Okay. All caught up. Let's Arcana says, yes, will this recording be available on my channel? Yes, it will. If you go to the live tab on my channel, it has all of the live streams that I did for Chegg for these Organic Chemistry 1 office hours. So those will be available. If you want to go back to the beginning, I start with nomenclature and stereochemistry, right? The really easy stuff. And then we get more complicated from there. Okay, moving on. All right, so which of the following compounds is chiral? And we have a few disubstituted cyclohexanes in their chairs. And so this is an interesting one because the easiest way to assess whether they're chiral is from the top-down view, right? So why don't we convert all of these from chairs to top-down line notation? So here we have this guy here. So let's just draw the cyclohexane. And now these chlorines, are two apart and they're trans to one another, right? This one is up and this one is down. So let's draw this one up and let's draw this one down. Okay. Now B, we have them, it's 1,4. And sorry, there's like an infestation here. Some bugs. Jeez. 1,4, and it's cis. So let's put a chlorine here and a chlorine here. Then we have 1,3 again, but it's cis. So let's put them both up. And then we have 1,4 trans. So this one is up, and the other one is down. So let's start with the ones that have no chiral center. This one does not have any chiral centers because the two directions around the ring are identical, right? Because of the symmetry of the molecule, there's no chiral centers. If there are no chiral centers, it can't be chiral. That's actually not entirely true. There are some very interesting exceptions. It is possible to be chiral with no chiral centers, but they're very weird molecules that we typically don't go into, and certainly not in OChem 1. So from the perspective of OChem 1, let's just pretend that what I said is true. If there's no chiral centers, it cannot be chiral. Same with here. The two directions around the ring are identical. So there are not 4 different groups. So there are no chiral centers here. So these cannot be it. There are no chiral centers. Those are not chiral. Now, these ones do each have 2 chiral centers. There are 2 chiral centers here. The only difference here is that this one is meso. There is an internal symmetry plane here. If we reflect half of the molecule across that mirror plane, we do get the other half of the molecule. And so that makes sense, right? If you took the mirror image of the molecule, you'd get the same molecule. And so it cannot be chiral. So a meso compound is an example of a compound that has 2 or more chiral centers, but is achiral overall, achiral or not chiral overall. So remember, if there are no chiral centers, it's not chiral, at least from our perspective in OChem 1. If there is 1 chiral center, it definitely is chiral. And then if it has 2 or more chiral centers, it may or may not be chiral depending on if there is any internal symmetry. And if there is internal symmetry, like a meso, if it's like an internal plane of symmetry generating a meso compound, or if there's an inversion center, which is a point of symmetry, a central point of symmetry, then it has chiral centers but is achiral overall. But this is chiral, right? We have 2 chiral centers, and there is no internal plane of symmetry, because if we tried to do this, right, if we tried to do the dashed line down the center, that doesn't work because the wedge chlorine would be reflected onto the dash chlorine, or vice versa. And so that's not the same. So that actually is different. So this has an enantiomer, right? This has an enantiomer, which is the mirror image of it, which is not the same. So that would be, if you put the dash here and the wedge there, that actually is a different molecule, right? Structurally the same, but in terms of stereochemistry, it's the enantiomer, it's the mirror image. So A is the chiral one. Okay, let's move on. Let's just do a quick nomenclature, because if you guys got finals coming up, you may have to be doing some nomenclature, so we want to review a little bit. So what are we going to do with this here? We have we have a hydrocarbon, we have 2 bromo groups, and we have 1 hydroxyl group. So we know that this is an alcohol. Right. The hydroxyl group is the highest priority functional group on here. It alters the properties of the molecule such that we consider it to be the most important functional group on the molecule. So it will determine the numbering of the parent chain. Right. So there is a hierarchy here. So if with hydroxyl and then alkyl and halogen are lower priority. Hydroxyl is higher priority, which means that we will number the parent chain. Number one, the parent chain has to contain the hydroxyl. It has to contain the carbon that bears the hydroxyl, even if there's a longer chain elsewhere in the molecule. And number 2, we will number that chain so as to give the hydroxyl occurring soonest, even if numbering the other way would give some other substituent sooner. So in other words, we've got this parent chain, right? This is the longest carbon chain that contains the carbon that bears the hydroxyl. That has to be in there. So we would not do these, right? It would not be these ones. It's got to contain this carbon. So that's the longest chain. And now we are going to number so as to give the hydroxyl occurring soonest. Even if, right, if this bromine was on the terminal carbon over there, we still would number from the left, right? Because the hydroxyl beats it, right? If we were comparing alkyl and halogen, then it's just whichever is soonest. But hydroxyl takes priority. So that means we are going to number it this way. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. That's the numbering scheme, not the other way. Even if we had a bromine over here, which would make it on carbon 1, numbering the other way, doesn't matter. Hydroxyl takes priority. We number left to right. So we've got the parent chain. We've got the numbering scheme. Now we have to list the substituents. We have 2 bromo groups on carbon 6. So we have 6, 6 dibromo. So remember, it's 2 bromos, so we include the prefix di. The di is not included in alphabeticity, but these are the only substituents right now, so it doesn't matter. So 6,6-dibromo 2-octanol. Can also be octan 2-ol. Equivalent, doesn't matter. I prefer this, 2-octanol. Looks cleaner to me, but this is also equivalently valid. So we identified the parent chain, which has to contain the carbon bearing the hydroxyl. We numbered left to right because it gives the hydroxyl specifically occurring soonest. Then we list the substituents, followed by the parent molecule, indicating where the hydroxyl can be found. It's on carbon 2, so 2-octanol. Let's see. Kerplunk asks, how would you know it's enantiomerically pure? Just in general, how would you know if something is enantiomerically pure? You could do optical analysis on it, right? You could see if it's optically active. Optical activity will tell you whether you have whether it's chiral or racemic mixture or something in between. Bucky asks about some enolate chemistry. Sure, you can have an enolate can attack an aldehyde or a ketone as well as an ester. That's true. So you can have mixed clasins, just like how you can have mixed aldols, right? If you have an aldol where you have an aldehyde and a ketone, the aldehyde can enolize and attack the aldehyde. The aldehyde can enolize and attack the ketone. The ketone can enolize and attack the ketone. The ketone can enolize and attack the aldehyde. So when you do aldols, right, usually chemists will be very strategic and make one of them not enolizable, like benzaldehyde or something, so that can only be attacked. It cannot become the enolate. Same with clasin, right? There can be crossed clasins as well. And then also Dieckmann's, right? There could be the intramolecular version competing depending on how many carbons are in the molecule. Oh my gosh, wow, I completely missed these other substituents. Wow. Talk about brain fart. That's ridiculous. Okay, thank you for alerting me to that. Let's just go ahead and erase this then. Okay, so we have a methyl on 4. Whoops, stop it. We have an ethyl on 3. Okay, now let's actually name it. So what comes first alphabetically? You have bromo, you have ethyl, and you have methyl. So bromo is going to come first, 6,6-dibromo. Then we have to do ethyl, 3-ethyl. Then we do 4-methyl. And then we do 2 octanol. So that should all be one line. I just ran out of space. Thank you for that. I can't believe I just totally spaced on that. So we found the parent chain. We identified all of the substituents. We had two bromos. We had one methyl. We had one ethyl, and then we listed them alphabetically. So remember, dibromo is B for bromo. If we had chloro as well, it would still be dibromo before chloro because it's B for bromo, not D for dibromo. That's just a very common error. So dibromo, and then the ethyl, and then the methyl, and then octanol. Thank you for that. Okay. Okay, Aisha asks about the acidity of aromatic molecules. So normally, so it depends what you're talking about, but like, for example, if we're comparing toluene and phenol, right? There's a big difference here. Or even how about this so that we're not comparing. So let's compare the same uh atom, right? We're going to an oxyanion. Um if we have this, right? This versus, I'll draw all the bonds here. Whenever we're looking at aromatic compounds, we have to be aware of the possibility of resonance. So, right, there's so much resonance that can happen here. That's why phenols are pKa like, what is it? I want to say 10, something like that. It's you double check me on that, but I think it's somewhere within a couple orders of magnitude of 10. But that means it's about 1,000,000 times more acidic than water. So why is that, right? Because if water deprotonates, you're left with an oxyanion. If phenol deprotonates, you're left with an oxyanion. But the difference is the incredible amount of uh, resonance, right? So this negative charge can be distributed around the entire molecule. It's quite diffuse. So that's just what I think of off the top of my head, right? I don't know what examples you're thinking of, but usually it's ones where the resulting conjugate base is heavily resonance stabilized through the aromatic ring versus not. Something like that might be what you're looking at. Okay. All right, let's get rid of this. Okay, now we're going to do, it's very similar to the other one that we just did, right? Let's practice another one here. It says, given the following IR and NMR data, so it's the same thing, right? But now we have this formula C4H10O. C4H10O. So what did we do last time? What did we do? We looked at the IR data to find a particular functional group that will tell us what the oxygen atom is doing, right? Because right now we don't know. And then also another important thing here is that we have no degrees of unsaturation, right? Because this fits the CnHn plus 2 formula. So there are no pi bonds. So that already, we're thinking oxygen probably is not a carbonyl oxygen. But we can go ahead and confirm it here because apart from the saturated CH stretch, right? We have the saturated CH stretch, but again, that's going to be on almost any organic compound. But over here, we have the OH stretch. So this is important, even just from the molecular formula, we probably were ruling out carbonyls, and we see that there's no carbonyl stretch. So if there's no carbonyl stretch, there's no carbonyl. But seeing the hydroxyl stretch tells us this is an alcohol, not an ether, right? Because an ether could also fit, right? Without the IR data, if we're just looking at degrees of unsaturation, there's no degrees of unsaturation. An ether oxygen does not generate any unsaturation. That's just right there in between the carbons. But we're ruling that out. We're saying there's got to be a hydroxyl. There's one oxygen, there's a hydroxyl. The one oxygen is in the hydroxyl group. Has to be, right? So if we have a 4-carbon molecule with a hydroxyl, let's see, we could have this. We could have this. We could have this. We could have this. I think that's it. I'm pretty sure that's it. That's the only ones that come to mind. So we have the straight chain. We can have 2 straight chains. It's only 4 carbons, right? So with only 4 carbons, you can have straight chain hydroxyl terminal, straight chain hydroxyl internal, right? If we move this to this one or this other one, it's the same compounds again. Doesn't matter. Then you can have, you can just move 1 carbon over, right? We can have we can have the isobutyl version, and then we can have the one here with there's only one possibility for a tertiary alcohol, so that would be that one. So these are the 4 that come to mind. So let's do what we did. I think this is the easiest way to do it. If you use IR data to come up with all of the possible structural isomers that could potentially fit, then what you could do is predict the number of resonances. That's it. We don't have to look at splitting or chemical shift or integration. Just how many peaks are you going to get? That's it. And let's figure it out. Right here, we're going to have 1, 2, 3, 4, 5. Right. So that doesn't look too good. Over here, how many are we going to have? We're going to have the hydroxyl proton, and then we're going to have all of these methyl protons together, right? These are all equivalent. We would have a singlet integrated to 9. So this would be very obvious. If it was the tertiary alcohol, it would be an extremely simple spectrum. It's almost certainly cannot be this one. Over here, we've got 1, 2, 3. There's 1 implied hydrogen there. 4, 5. Again, 5 peaks. So maybe there's something wrong with our analysis here. 5 instead of 4. It could work, but probably not. But then over here, what do we have? We have 1, 2. There's 2 protons there. 3, and then 2 identical methyls make 4. Okay. So this, now let's just go ahead and assume it's this one, right? And let's go ahead and assign the peaks. If something goes wrong, we can always go back. We can always go back and say, oh man, did I make a mistake? Like, did I miss some equivalent groups of protons? Right? Did I mess something up there? Did I miss a possible structural isomer? Maybe I forgot one possibility. But from this first analysis, it seems like it has to be this. So let's just redraw it. Let's get rid of all this and redraw it with all of the implied hydrogens. So we've got 2 hydrogens here. We've got 1 hydrogen there. We've got these methyls, these methyl hydrogens, these methyl hydrogens. So what are we going to expect? Okay, this one we're going to expect it is going to be a 1H singlet. That just happens to typically be the case for hydroxyl protons. Over here, we've got a 2H doublet, right? We've got one proton next door, so that's going to end up being a doublet. Then we've got a 1H multiplet. This is going to be exceedingly heavily split, right? We've got 3, 6, 8 neighboring protons. So we're looking at upwards of 9 smaller peaks. It begins to become not even that discernible. All we know is we're just going to call it a multiplet. It is a heavily split resonance. That's good enough. And then over here, we have a 6H doublet because all of these are split by the one neighboring proton. So let's call these A, B, C, and D. And now let's make our assignments. Let's also talk about chemical shift. The hydroxyl proton should be the most downfield because it's directly bound to the oxygen atom, right? Next should be this 2H doublet because it's right next to the oxygen. Then would be this guy, the 1H, and then the most upfield should be these 6 methyl protons. They are the furthest away from the oxygen. So let's see if this assignment works out. We have, look at this, we do have a doublet. It is integrated to 6H, and it is the most upfield. That looks great. That's going to be D. Then we have this very heavily split 1H there. And so that makes perfect sense, right? And it also makes sense that it is the next one going downfield because we're moving closer towards the oxygen atom. So that is going to be C right there. Then we have the integrated to 2, the doublet. That is quite a bit more downfield because now we're immediately adjacent to the oxygen atom. So that is going to be B. And then we have our singlet integrated to 1. That is our hydroxyl proton. So that is going to look like that. So that is important to note that hydroxyl protons, they don't really participate in splitting the same way that the ones on carbons do. It's a little bit funky. It becomes different. So you can just get used to hydroxyl protons. Usually they're appearing typically as singlets there. So that's it, right? We did our assignment. Once again, what did we do? We looked to the IR. First we looked at the molecular formula to figure out the number of degrees of unsaturation. Fit the CN HN plus 2 rule or format. So no degrees of unsaturation, no pi bonds, no rings. Then we looked at the IR and we said there's a hydroxyl in it. This is an alcohol. We drew the 4 possible 4-carbon alcohols, right? That was all the ones that we could think of. We figured out on the basis of predicting how many peaks they're going to produce alone. We didn't look any further than that. We only had one that was going to create 4 resonances. Then we expanded. We did our assignments. We did our predictions of integration, chemical shift, and splitting. Then we looked and we saw that all the data agree with that assignment. So that was it. Okay, let's see. Got it. Okay. Time for one more really quick, super fast here. Draw the most stable conformation of trans 1-ethyl 3-methyl cyclohexane. So let's draw 2 chairs. We'll draw both the chairs, and then we'll see which one is better. So there's one chair. There's the other. So I'm going to take, so when you put the first substituent on there, you can put it on any carbon and you can put it up or down. That is arbitrary. Then from that point forward, the rest is not arbitrary. You do have to know what's going on. So trans 1-ethyl. So let's do up. And then that means if we go clockwise, 1, 2, 3, now we have a methyl going down. So there's our methyl down. Then over here, if we do the ring flip, that means, or the chair flip, this was the ethyl on the leftmost carbon going up. Here is the leftmost carbon going up. We get the ethyl now on the equatorial. And then over here, we have the methyl going down. So we're going 1, 2 carbons over, and here's our methyl going down. So what's the difference here? We have an ethyl axial and we have a methyl equatorial. And then over here, we have an ethyl equatorial and a methyl axial. So the bulkier the group is, the higher the premium there is on getting that in the equatorial position. And so this is more energetically favorable right here. We've got the ethyl equatorial and the methyl axial. That is better than having the ethyl axial and the methyl equatorial. That will be a lower energy conformation. Okay. So that's it. Thanks again, everybody. So that was a great semester here. Once again, this was the last of these office hours with Chegg for Organic Chemistry 1. But hopefully we will see you next semester. If everybody informs Chegg how informative and helpful these sessions were, I'm sure they will bring them back. So hopefully I will see you in the fall semester for Organic 1 or Organic 2 or whatever they want.